would like to ask a question. Again.
Good afternoon or good morning, depending on what time zone you happen to be in. It's 1:30 Eastern, 12:30 Central, and earlier in the morning for all of you in the Pacific and Mountain time zones. I'd like to welcome you to webinar number 9, HSM Applications to Rural Multi-Lane Intersections. We've got a 3-session webinar for you today. In getting started, if you'd be so kind to indicate in the poll pod in the upper right of the welcome screen how many people are in the room with you on your call-in line. It would be very helpful to us at FHWA. We do try and identify how many people are participating in each of our webinars, and this is information that's helpful to us. I do want to call your attention to the pod for the file share that's on the right-hand side of your screen, as well as the links to the recorded sessions for previous HSM webinars on the right. And we will put these up at the end of today's webinar in the wrap-up room so you can avail yourself to them. We're going to hold questions for today's webinar until the end. You can pose your questions during the webinar in the chat pod on the left-hand side of your screen, or you can at the end of the webinar pose a question, and we'll open up the lines to each of the questions. And with that, I'm going to move us over to the presentation room and get started with today's webinar. Session number 1 on the introduction to the Highway Safety Manual, Rural Multi-Lane Intersections, will be presented to you by Tim Taylor, Safety Engineer with FHWA's Resource Center. And go ahead, Tim.
Thank you, Fred. Welcome to everybody for this 9th in a series of, I think, about 12 webinars on the Highway Safety Manual. Today we're going to be looking at the applications to rural multi-lane intersections. Session 1 will be basically a overview. So we'll get started. Here you basically see the series of webinars that have been offered. We're at number 9 again. Tomorrow there will actually be another webinar on horizontal curves. That will be number 10. Today, the instructors will be myself, Tim Taylor, with the FHWA Resource Center, Fred Rank, who gave the introductions, and Gene Amparano, also of the FHWA Resource Center in Kansas City. This is session 1, which is basically introduction and background to the rural multi-lane intersections applications of the Highway Safety Manual. In this first session, what we hope to do is to review the crash frequency performance of rural multi-lane intersections, that is the safety, and also define the substantive safety that can occur beyond the nominal safety effects. When you look at the total of multi-lane highways, both rural and urban, we have approximately 4 million miles of public roads, nearly 1 million miles on the federal aid system, and about 166,000 of those multi-lane highways, or about 17%. About 45,000 miles are multi-lane undivided, which make up about 27%. And then a bulk, or 121,000, are multi-lane divided, or about 73%. So there are more divided multi-lane highways than undivided. And that's what we're going to be looking at today, are the multi-lane divided. When you look at rural expressway mileage, predominantly larger states have more miles rural expressway mileage. As you can see on the screen, Texas being first, Virginia, New Mexico, and on down the list. Texas has about twice as many miles as the next closest state, which is Virginia. But there is a vast amount of rural expressway mileage. Crash rate on rural expressways, based on a MnDOT study, there's approximately 9 crashes per million vehicle miles. But the crash rate on the rural expressways is less than that for the rural 2-lane highways, which is approximately 1 crash per million vehicle miles. The severity on rural expressways, approximately 1.2 deaths per 100 million vehicle miles, is less than for the rural 2-lane highways, or at 1.5 deaths per 100 million vehicle miles. Now, some states are going to have higher crash rates per million vehicle miles than this. I know some are over the that 0.9 level, and some are certainly over the 1.0 crashes on 2-lane highways. But on average, this is what we can anticipate, even though your state or your area may be a fair amount higher than this. One thing we have learned is that when access density is low, then the crash rate is similar to rural freeways, which is about half of what we experience on 2-lane highways, or about 0.5 accidents per million vehicle miles. So again, it's a function of the low density of traffic, and there are other factors that can enter into that as well, besides the low density, the level of development, commercial development, and that nature. This table just illustrates the Nebraska crash experience of 2-lane highways versus 4-lane expressways, which we're dealing with today, the 4-lane expressways. But we can see that if you look at all crashes, as far as the fatalities, they're significantly higher on the 4-lane divided highways. The difference is about 31%. So if you'll note that the crash rates for 4-lane rural divided expressways are significantly lower for the fatals and somewhat lower for injury, and actually more than the rates for the 2-lane highways that are planned for conversion to a 4-lane divided. In 2008, of the U.S. total intersection crash characteristics, there's a significant amount of accidents that are occurring at intersections based on the highlight there. And we find that this number is overrepresented because 57% of fatalities and serious injury crashes that are occurring at intersections, which is an overrepresentation based on the number of miles or segments versus intersections. When we look at crashes by divided and undivided highways, we see that that the crashes for the unsignalized divided expressways greatly outnumber the crashes for the signalized divided highway intersections, approximately 56.5% at unsignalized locations. That two-way stop control intersections, which is very typical of intersections you find on rural divided highways. This graph shows the percentage of intersection crashes in Iowa for their expressways, 39% intersection crashes when the ADT is over 10,000, and that relates closely to what we saw from the earlier slide, which shows there's about, when you tracked out the unclassified crashes, when you combine the signalized crashes versus the combine those with the two-way stop control intersection crashes, then you'll find that you have about 39 to 40% of the crashes are occurring at intersections. Again, a MnDOT study, expressways. This too comes from the NCHRP report 650. The Highway Safety Information System, or database, was used for this study. And in examining the existing data for the 5 states in the system, which Iowa and Minnesota were included, it's now been expanded to 8 states. It was determined that supplemental information on roadway access points and roadside condition would be needed. And one efficient way to collect this type of data is through the video disc photo logs. And the photo log simply contains the images of the roadway taken at 16-meter intervals. And then these images can be randomly accessed in seconds under the control of the microcomputer. At the time this study was conducted, the video disc photo logs were only available for Minnesota, and so consequently only data from Minnesota were used for the statistical modeling analysis. And data for the accidents reported from 85 through 1990 were used for this study. Things came out of this study that were significant, one of which was that 87% of right-angle crashes were due to the inability of minor road drivers to recognize the oncoming expressway traffic, and or the ability of the drivers to select a safe gap in the expressway traffic stream. The other thing that was noted was that 78% of the right-angle crashes were far-side type collisions. That is, a right-angle crash involving left-turning or crossing minor road vehicles that successfully cross the near-side intersection across the median, but then collided with an oncoming vehicle on the far side of the intersection. This will be illustrated in the next slide. But the third thing that was found from this study is that intersection recognition was important, and that is, we may think that running of the stop sign was a major contributing factor. So the recognition by the drivers on the minor or the stop controlled approach was not, in fact, a contributing factor in any of these right angle type crashes at these intersections. And another study found that the ratio of the far side versus the near side collisions at 30 two-way stop control rural expressway intersections with the highest crash severity indices in Iowa was 62% to 38%. However, at 7 of the intersections where horizontal curves were present along the expressway, the far side and near side collisions were nearly equally distributed at 51 and 49% respectively. So therefore, it looks like horizontal curves on the main line seem to create a unique hazard for the minor road approach. And this illustrates the near side versus far side. So if north is up and south is down, a vehicle on the north or the southbound approach colliding on the first roadway would be a near side intersection, and colliding with a vehicle again southbound on the far side intersection on the other roadway would be considered a far side intersection. And again, most of the difficulty occurs for motorists who are on the side street negotiating the far side intersection versus the near side intersection. And one of the reasons may be that they have a refuge in the median. These two pie charts simply illustrate that expressway two-way stop control intersections experience nearly twice as many crashes as do other typical rural intersections. And nearly twice as much are attributed to those type crashes, and a lot of times almost half of those right angle crashes are related to gap acceptance. So in other words, vehicle pulling out into the intersection has misjudged the available gap, and therefore has a right angle type collision. Key safety principles and design. We all know that knowledge is imprecise, but judgment is essential. Meeting the standards does not necessarily make a highway safe. Some of the important features of highways are not determined by the standards, such as alignment of left turn lanes, and whether they're angled or parallel, spiral transitions to curves, or the use of center two-way left turn lanes. So we know that meeting the prevailing highway design standard does not necessarily make a highway safe. The word standard gives rise, of course, to sometimes misinterpretation. We often think of a standard as usually being understood to be a guarantee of some degree of quality. Conversely, if something is substandard, then it's understood to be deficient. So implied is a distinct difference between what is good and acceptable and what is bad and deficient. And this meaning does not apply to highway design standards in their relationship to highway safety. And that's a little bit of a new way of thinking, but is one that is necessary with the advent of the Highway Safety Manual. So the safety of a highway does not change abruptly when some highway dimension changes slightly. In addition, highway design standards evolve with time, and highway design standards are not a demarcation between what is safe and unsafe. Many highway design standards are limit standards as we know them, and just meeting them does not necessarily make the highway safe as it can be. So it is a sign of an ungenerous design that may or may not be justified. Important features of the highway are not determined by standards, yet they affect its future safety, as is shown in the slide here. And some of those things are the distance between intersections that aren't determined by standards necessarily, use of spiral transition to horizontal curves, and other things. That leads us again to the discussion of nominal safety versus substantive safety. And if you've been involved in webinars in the past, you're probably familiar with this. But just to repeat for those who are not aware of it, nominal safety refers to reference to compliance with standards, warrants, and guidelines and sanctioned design procedures. And substantive safety is the expected or actual crash frequency and severity for a highway or a roadway. This term, nominal safety, was coined by Dr. Ezra Hauer. It was used to describe the characterization of a situation in terms of its adherence to design standards and practices. But we can think of a road as being nominally safe if it meets the minimum standard of care and is current with respect to published standards and guidelines. On the other hand, the term substantive safety, or perhaps a quantitative approach to safety, is its actual or expected performance in terms of crash frequency and severity. So, it begs the question, are the two dimensions of safety the same, or do they express related yet fundamentally different information about a highway? So, when we consider nominal safety, we want to know, is it based on research and operational experience? Does it provide the consistent level of quality? Is it reflective of the general cost effectiveness? And is it going to provide protection from claims of legal liability? That's basically the first step. Have we complied with nominal safety? And that's simply a yes or no question. An example of this concept is that AASHTO says a nominal shoulder is 6 feet and an 8-foot shoulder has a crash modification factor of 0.87. And from NCHRP 486, to illustrate the difference between nominal and substantive safety. The base conditions or the safety performance function for a design, AASHTO design, is a 12-foot lane with a 6-foot shoulder, where there is a safety shortfall, such as where we may want to pave the shoulder and add a shoulder rumble stripe instead. This could reduce the runoff road crashes. So an example of this is shown by a nominal safety would be providing a left turn lane on major approaches where we could expect crash reductions. A substantive safety measure would be to use a positive offset for the alignment of the left turning lanes, where we could expect a 23 to 50% additional fewer total crashes. So the purpose of this portion of the module is to clearly describe the workshop to the participants. The safety effects can be measured and quantified just as the effects of capacity have been for years measured and quantified using the Highway Capacity Manual. As practitioners, we need to fully understand and quantify intersection operations and safety performance in the pursuit of informed and balanced decision-making. Methods to quantify capacity operations have been in use since the late 1950s up until the most recent edition of the Highway Capacity Manual, and these methods for operational assessments are well documented and in widespread use. So methods to quantify safety are now taking form based upon the research compiled in the new Highway Safety Manual. What is the Highway Safety Manual? It's like the Highway Capacity Manual. The Highway Safety Manual describes the mathematical relationships for safety performance based upon exposure and roadway conditions. A Highway Safety Manual is an analysis tool only, just like the Highway Capacity Manual. And the Highway Safety Manual does not have standards nor best practices guidance. The Highway Safety Manual does not supersede other publications that do. It's not going to tell you what actions to take and what actions not to take. Versus other documents such as the MUTCD or the Green Book, AASHTO Green Book, these do represent standards which have to be adhered to. So the Highway Safety Manual is a set of tools for prediction of crash frequency and for analysis of safety, and it facilitates explicit consideration of safety throughout the project development process. It provides a synthesis of validated highway safety research over a number of years. It provides analytical tools for predicting the impacts of decisions that we make every day on road safety. New Highway Safety Manual of 2010, it contains the best science and research, as I said, over a number of years, going past a decade or more. It's a synthesis of previous research, and it also includes new research that was commissioned by both AASHTO and FHWA for use in the Highway Safety Manual. What can the Highway Safety Manual do for you? Currently, we're quantifying environmental impacts. We're quantifying operational analysis through use of Highway Capacity Manual and other tools. And we're performing economic analyses. The Highway Safety Manual will allow us to add safety impacts to also quantify these in consideration of project development, programming, operations, and maintenance. How can a crash prediction be used? Well, any number of ways. As I said, at the program level, to prioritize segments or locations for selection of projects and upgrades. At the project level, to assess the relative needs for a project and to communicate the relative needs to the public in numbers now. Prioritize work to keep project within budget, and to provide supporting documentation for design exceptions. And it can also be used for tort defense if used properly. This tool can help quantify the relative safety of a facility and demonstrate that an agency is addressing those safety needs appropriately. Considerations of safety in the design process. It is the policy of FHWA that safety must be fully considered in every aspect of all of these phases. In July of 2004, a memorandum by Administrator Peters cited safety as the main priority of the DOT, stating that I fully support Secretary Minetta's view that safety is the main priority of the DOT. We need bold actions and initiatives that will lead to a significantly safer road network, end quote. To achieve the DOT national fatality rate goal of 1 by 2008, safety must be fully considered in every aspect of our business, from planning and programming, environmental analysis, project design, construction, to maintenance and operations. We have to use data-driven decision-making and ensure that safety is a key input in any decision made in the project development process. FHWA must also assert its influence even beyond its traditional federal aid program responsibility, as a major portion of the nation's safety challenge is on the federal highway system. It's particularly important to assure safety is fully considered in the preliminary design phase as project options are being advanced and environmental analysis is underway. When safety is identified in the purpose and needs statement of an environmental document, then it should be supported with specific crash data to create a quantifiable basis for enhancing safety on the project. And when evaluating alternatives, there should be an emphasis on identifying and analyzing safety impacts. The preliminary design phase is also a good time to develop and conduct a road safety audit, particularly where crash data suggests a significant safety problem exists. A road safety audit provides project designers a broad, multidisciplinary set of perspectives that will add important insights and define the strategies that will address whatever critical safety challenges of the project exist. So, balancing safety with many other factors is critical to good design decision-making in the planning and preliminary design phases, and it is a requirement. So what is the role of road design in crash prevention? Design can reduce the incidence of human error, the chance of human error resulting in a crash, and the severity of the consequences of crashes if and when they occur. So how a particular section of highway or street or intersection is built, the engineering, and how it is operated affects both the number and severity of the crashes. So consider, it is natural to blame drivers for crashes, but it is decidedly untrue that most crashes involve bad drivers. Nor does it follow that driver training and testing or education, regulation, or traffic law enforcement are the only or most effective ways of reducing future crashes. How a particular highway is built determines the number and severity of the crashes on it. This is why building safety into highways is so critically important now. So what can the Highway Safety Manual do for you? It can predict the safety performance of geometric design features. Quantitatively calculate the safety effects. And it can predict the safety performance of intersections, which is our focus today on rural multi-lane highways. All the above. It can also provide better decisions for safety, obviously. So the learning outcomes to review the crash frequency performance of rural multi-lane intersections, just a brief overview of that, and also compared substantive safety versus nominal safety and how we go above simply providing nominal safety. Okay, at this time, I'm going to turn it back over and we'll go to session 2.
Thank you, Tim. My name is Gene Amparano with Federal Highway Administration. I noticed that we have a small rectangle that's blocking some of our text on our slides. But the only way that we can get rid of that small box is if we close out the presentation and open it up. You don't have to do anything, but it just takes a second. So let me do that, and then what happens is that comes back in, and that layers over that little white triangle. So Just give me a second here and I'll pull them back up. And then we'll be on our way, and you won't have that little white box blocking some of the text. Okay, now that we resolved that problem, we're going to move on. This is session 2, and the main focus of this session is to talk about the prediction of crash frequency for rural multi-lane intersections. So we're going to describe the models to predict crash frequency, and when we say models, we're talking about safety performance functions that are identified in the Highway Safety Manual. And then we're going to walk through a couple examples of how to use those safety performance functions to come up with a crash frequency for base conditions for a rural multi-lane intersection. Before we get started on that, we need to define what a rural multi-lane highway is. It applies to 4-lane undivided and divided rural highways. And rural is defined as places outside the boundaries of urban areas where the population is less than 5,000 persons. Okay, so basically it's any highway located outside the city limits of an urban area above 5,000 persons is considered rural. And it can be difficult to determine at times, so you'll want to approach this with a little bit of caution, but you should be okay. Multi-lane facilities are defined as facilities that have 4 through lanes. They can be divided with a rigid or flexible barrier or with a paved or a landscaped median. They should not have access or egress limited by grade-separated interchanges. In other words, they should not be freeway-type facilities. But it's okay to have an occasional grade-separated interchange, but they shouldn't be the primary form of access or egress. There are some limitations on the methodology. This is the first edition of the Highway Safety Manual, and there are some gaps. And there's a current TRB committee underway that is already looking at these areas and trying to identify the gaps and ways to fill them. And those gaps will be filled or provided in future editions of the Highway Safety Manual. Currently, the safety performance functions and crash modification factors that will being presented today is based on relationships that are well understood, where there's significant research that's been conducted that helped develop these particular mathematical models that we use for crash prediction. They are a statistical model, treats the effects of each geometric design element and traffic control feature independently, and ignores any potential interaction between them. There are safety performance functions, and there are separate functions for highway segments with homogeneous characteristics, meaning same type of lane width, shoulder type, cross slopes. And then we have separate safety performance functions for intersections. On July 7th, the safety performance functions and crash modification factors for highway segments of rural multi-lane highways were presented. And today we're going to present those same safety performance functions and crash modification factors that are identified for intersections out of the Highway Safety Manual. A segment can begin or end anywhere along a roadway, but if the segment was being analyzed between 2 intersections, then the analysis point of this segment should begin and end at the center of those intersections. Also, the slides talks about the importance of assigning crashes appropriately to either segments or intersection crashes, And the way the Highway Safety Manual recommends is that if you're within the physical limits of the intersection, which could be the curve radii or the crosswalk limits, then that's identified as Area A. Then those crashes that are occurring in Area A would be identified as intersection crashes, and crashes occurring outside of Area A would be assigned as segment-related crashes. But some state agencies have identified specific distances from the center of an intersection. For example, some states choose 250 feet, some choose 200 feet as a distance from the center of the intersection, where they assign that crash that occurs within that distance as being a crash-related, intersection-related crash, and those that are outside the area as a segment-related crash. But check with your agency, see what your particular agency specifies, and just be careful that you assign the appropriate type of crash to the appropriate section. And just because it does occur within the extended limits of the intersection, sometimes you'll have to even take a look at the crash report itself to identify it as either an intersection or a segment-related crash. Intersections are defined as the general area where two or more roadways join or cross. There's different types of intersections. They can be signalized, they can be stopped and controlled, or they can be roundabouts. Currently, the Highway Safety Manual does not have any safety performance function on roundabouts, but we do have safety performance functions for signalized and stop-controlled intersections. The Highway Safety Manual further defines intersections as physical areas. Again, that's being within the physical contents of the intersection itself, which could be the limits within the curve radii or the crosswalk limits, but they're also identified as a functional area. And in the Highway Safety Manual, the functional area extends both upstream and downstream from the physical intersection area, which includes the auxiliary lanes and any channelization that happens to be present. And they're listed into three basic elements. That's the decision distance, the maneuver distance, and the storage distance. And here's a diagrammatic view of what a functional area would look like. The decision site distance: as the driver approaches the intersection, he makes a decision of what he's going to do, whether he's going to make a turning maneuver or proceed through the intersection. Then the maneuver distance is that space where he gets in position to go through the intersection or make a turn movement, whatever case his decision may be. And then, of course, the last segment or element of the functional area of an intersection is the queue length or the storage distance required for stopped vehicles. The procedure for applying the crash prediction method at grade intersections, there's a couple of steps. We're assuming that you already have all the information that you need to do the prediction or the analysis, such as your traffic volumes, your signal type, or your intersection type, whether it's stop control or signalized, and anything that's geometrically associated with the intersection. And there's two steps. First is to apply the safety performance function model, which gives us a prediction for base conditions. This is the safety performance function for a multi-lane rural intersection. Then the second step, which Fred Rank will be covering, is that you take the safety performance function that is for a given set of base conditions. Then you apply crash modification factors that are associated with the geometric conditions of that intersection or traffic control elements to adjust your predicted value to a more realistic actual value. So this is what we're going to be talking about today. In this particular session is applying the safety performance function model for base conditions. The model applies to three types of intersections. three-legged intersections with stop control, four-legged intersections with stop control on the minor approaches, and four-leg signalized intersections. And the safety performance function is good for both divided and undivided rural four-lane highways. Again, this is our safety performance function for rural multi-lane intersection, wherein with subscript SPF-INT, which is safety performance for the intersection, is the expected number of intersection-related crashes per year for a given set of base conditions. The ADT major is the daily traffic volume on the major road. ADT minor is the daily traffic volume on the minor road. And the A, B, and C are regression coefficients out of the Highway Safety Manual from Table 11.7 or Table 11.8, depending on whether you're talking about stop control or signalized intersection. These are the base conditions for a rural multi-lane intersection. This is what our safety performance function is assuming, that the intersection angle is 0 degrees. In other words, the crossing roads are 90 degrees of each other. Also assumes that there are no left turn lanes present, there are no right turn lanes present, and there's no lighting present. And this applies for the stop controlled intersections. It does not apply to signalized intersections. There are no set base conditions for signalized intersections for the reason that the signal is supposed to control the traffic movement that would cause conflicts for these particular types of turning maneuvers or items that are present. This is a copy of Table 11.7 out of the Highway Safety Manual. It lists the A, B, and C regression coefficients for stop-controlled intersections, and they list them for a four-approach stop control and also a three-approach stop control. And this example that we're going to be walking through shortly, we're going to be looking at total crashes. So we would use the A, B, and C coefficients in the top line. But if you wanted to, you could use the coefficients for fatal and injuries if you wanted to come up with a predicted number of fatal and injury crashes only. Both four-way and three-way stop control intersections. This is Table 11.8 out of the Highway Safety Manual. It provides the A, B, and C regression coefficients for signalized intersections, both for total crashes and for fatal and injury crashes. Okay, so here's an example. We have a four-leg stop-controlled intersection. We have 10,000 vehicles per day on the major road, 2,500 vehicles per day on the minor road. So for a four-legged stop-controlled intersection from Table 11.7, our A regression coefficient would be 10.008. Our B regression coefficient would be 0.848. And the C coefficient, which was not listed, would be 0.448. And entering our traffic volumes and our A, B, and C regression coefficients into the safety performance function and performing that exponential calculation, we come up with a predicted number of crashes of 3.7 crashes per year for base conditions. Now, here's an example where we calculate the expected number of crashes for a signalized intersection using the same traffic volumes, but using the different coefficients from Table 11.8 for a four-leg signalized intersection. entering our values for our A, B, and C regression coefficients and for our traffic volumes. And performing that exponential calculation, we come up with a predicted number of crashes of 8.2 crashes per year. So, the procedure for predicting safety is number one, is the first step is to apply the safety performance function model for base conditions, which we walked through. The next step is to apply the crash modification factors and the calibration factor, if you so choose, to the SPF value to come up with a total predicted value of crashes for that particular intersection. And Fred will be covering crash modification factors in the next session. This is how they're related. The safety performance function goes into the lower equation where the CMFs are applied to come up with a predicted number for the total crashes. This is another photo or another view of the table 11.8, but the purpose of this is just to show you that there are some different ways to look at the severity of an intersection, and what we're talking about here is the severity index, and that can be calculated and it can be used to compare or look at an intersection to determine how well it's behaving. In NCHRP 486, the severity index for intersections, both rural intersections, two-lane, and multi-lane intersections, is around 40%. So if you do your crash prediction, or if you know your existing crashes, you can come up with a severity index. And for this example, we have a rural four-way approach, a signalized intersection, and it's provided traffic ADTs. And the total crashes come out to be 39.5 crashes per year. But the fatal and injury and fatal crashes is 13 crashes per year. So you can calculate a severity index by dividing your injury and fatal crashes by your total crashes. And in this example, it comes out to about 33%. And the national average is 40%. So just by looking at doing your crash analysis and calculating your severity index, you can come up with a severity index that can be used for different alternatives or even for existing roadways to determine or help to prioritize those particular projects for further safety improvements. So in this particular session, we walked through demonstrated the application of the safety performance functions and how to predict or calculate the crash frequency for a rural multi-lane intersection. So that concludes this session, and at that, I will turn it over to Fred Rank.
Thank you, Gene. I'm glad so many of you are still with us in today's webinar. If you haven't already got a sense of it, let me set the stage so you understand how rural multi-lane and rural multi-lane intersections in the Highway Safety Manual fit into the overall Highway Safety Manual. The richest set of known safety relationships is found for two-lane rural highways and their intersections and curves. The next richest, most complete, is for suburban, urban, multi-lane highways and intersections. The third, in the terms of the extent of the knowledge, is rural multi-lane. So the SPFs are rather thin. We only have a couple. And in this session, I'm going to present to you what we know about the crash modification factors that are in Chapter 11 of the Highway Safety Manual. It's not extensive. It is not large. This is the thinnest chapter in the entire Highway Safety Manual. It's the thinnest chapter in Part C. Now, for what we know about rural multi-lane is still more than what we have in the Highway Safety Manual for interchanges and interchange access. That chapter is over in Part D. It did not make it as a chapter into Part C because of the lack of rigor, because of the lack of current, known, well-supported research. So I wanted to give you how things fit into the big picture. Now, the CMS for rural multi-lane intersection are just a few, and here's what we know. In this session, we're going to cover these CMFs, and we're going to apply them in an example. Here are the items that we know affect safety of rural multi-lane intersections. Configuration, the number of approaches, is really important. You saw it in the SPFs that Gene introduced in the previous session. For the same amount of exposure, ADT, for stop control, one stop of the stem of the T for a T intersection versus a two-way stop for a four approach stop controlled intersection. We have for the T 9 conflicts, we have 32 for the cross intersection. It is for sure validated in the Highway Safety Manual that three-legged intersections are safer than four-legged intersections for the same exposure. Skew is a known effect. The more the skew of the intersection, the greater the crash frequency effect. Left and right turn lanes have a profound effect in reducing crash frequency, be they for two-lane highways, multi-lane urban suburban highways, and they have that same large, major, significant effect in reducing crash frequency for rural multi-lane intersections and lighting. Table 11-20 provides the CMS for three-leg intersections, and that minor leg stop control is one stop sign of the stem of the T. Table 11-21 is for four approach intersections in which there are two stop signs, not four, two stop signs controlling the minor approaches. And you'll notice that we have just four CMFs for rural multi-lane highways for either three-leg or four-leg stop control only. There are no CMFs in Chapter 11 for rural multi-lane highway intersections for signalized intersections at this point in time. The data sets, the known relationships, the available research were not strong enough, not robust enough to include that information in this first edition of the Highway Safety Manual. So the effect of skew. And skew is the difference between 90 degrees to the major road of our side road approach. So skew angle is the difference between our minor approach to 90 degrees. And I've shown in slide 3-5 the amount of skew for this skewed intersection, rural multi-lane divided. We have two equations, one for three-legged intersections, one for four-legged. Both are stop control on the minor approach. Skew is actually in degrees in terms of the value to insert into the equation. Our crash modification, this is the first crash modification factor for multi-lane intersections, rural. So for example, a three-leg, stop controlled, skew angle of 35. And 35 is a large amount of skew. Older driver research has indicated that skew should be limited to 15 degrees or less, particularly to meet the needs of older drivers and to reduce their crash effect. We know that when we get above 15 degrees, crash frequency goes up. We have a larger effect. The AASHTO Green Book still shows 30 degrees as maximum skew, despite the research provided to the AASHTO Green Book Standing Committee on Geometric Design. So we would expect a fairly large effect. And in fact, that's the case. Applying that to the formula, plugging in 35 degrees of skew, we see an effect of about 8.5%, or a CMF of 1.085. This is a fairly big effect. It is not as big as effect as it would be the case if this was for a two-lane roadway. Meets a two-lane roadway, undivided, that we saw from Chapter 10. So the same amount of skew, but over in a rural multi-lane has less effect. If it's 4 approaches, same amount of skew, our formula changes slightly. For the CMF, we plug in our 35 degrees, and we see an effect of about, well, 1.092 for our CMF, about 9.2%. So for the same amount of skew, the CMF is slightly larger, meaning more crashes, crash frequency is increased for a 4 approach at 35 degrees in comparison to a 3 approach with 35 degrees of skew. Our second effect is for left turn lanes. Remember that left turn lanes remove the vehicle from the inside fast moving through lane, mitigate the rear end conflict possibility, allow the driver a safe place to select a gap in oncoming traffic to make a permissive left turn. Table 11-22 provides the CMS for left turn lanes in terms of 1 approach and 2 approaches. And mind you that these effects are for left turn lanes on the non-stop controlled approaches, meaning the through approaches to our divided rural multi-lane intersection. For a 3 approach with 1 left turn lane, a CMF of 0.56 is a 44% reduction in crash frequency. The big 3 in highway safety for rural intersections are left turn lanes, warning signs, and lighting. 2 of those 3 appear in the CMFs for rural multi-lane intersections in Chapter 11 of the Highway Safety Manual. For a 4 approach, 2 left turn lanes, we see an effect of 0.52 or a 48% reduction in crash frequency associated with left turn lanes on the through non-stop controlled approaches. Again, left turn lanes are a major significant safety countermeasure for rural intersections, multi-lane. Right turn lanes also have an effect. It's not as large, 0.86 for 1 approach, for a 3 approach intersection. For a 4 approach, 2 approaches having right turn lanes on the non-stop controlled approaches, we see an overall effect of 0.74 for a CMF, which would be a 26% crash reduction. Our 4th effect is lighting. And for rural multi-lane intersections, the CMF is stated as 1 minus 0.38 times the proportion of total crashes for unlighted intersections that occur at night. And that proportion comes from table 11-24. Not much difference in the proportion value between a 3 approach and a 4 approach rural multi-lane in terms of nighttime crashes. There is no value for a signalized intersection with 4 approaches in Chapter 11 of the Highway Safety Manual. So an example for lighting. Our 4 approach intersection, our value would be 0.273. Plugging into our equation, we get a CMF of about 0.896, which is about a little over 10% reduction in crashes. And remember, now this is the key thing. Lighting affects primarily crashes that occur at night when there's less traffic and less hours of daylight than there are times that they are light during the daytime. So we have less exposure, so we don't expect an effect on total crashes by lighting up the intersection at night when there's less traffic to be a huge effect. This is an effect of total crashes. Almost all of the CMFs, the known safety effects in the Highway Safety Manual, are implicit, assumed to be for total crashes. Only in a few cases do we identify a CMF for a specific crash type or pattern. And that's the case here. Normally we would expect an effect of lighting to be about 30% crash reduction. Not untypical, well documented in the research and in safety studies. But looking at the proportion of crashes occurring at night, we don't have that big an effect on overall crashes. And it clearly comes through in this application example. For example, we have a four-leg rural unsignalized intersection. That means it's stop control. That means it's two stop signs of the four approaches, and those stop signs face the minor approaches. 10,000 ADT meets 2,500 ADT. This is not entering volume. This is the ADT of the major road or the minor road. If we had 10,000 ADT on one of the major approaches and 9,000 on the other approach, we would always use the higher number. If on the side road, one side had 1,000, the other side had 2,500, we would use the higher of the value, in this case 2,500. 35 degrees askew. We've got left turn lanes on the major approach, a right turn lane on the major road, and we have lighting. So our predicted value, in working through as an example from our SPF that Gene showed you the example in session 02, is 3.7 crashes per year. Now, in applying our CMFs for skew, left turns, right turns, and lighting, the values, our skew is 1.092 from our previous example, left turns 0.52, right turns 0.74, and that left turn CMF is for two left turn lanes on the two major road approaches. It would be less if we only had one. And our value for lighting is 0.896 from the previous example of the previous slides. Applying the CMFs in a multiplicative manner to our 3.70, we get a overall predicted crash frequency for each of the effects of 1.39. Why, that's less than half the crashes we predicted for the base conditions of 3.70 using the SPF. So the overall effect of skew was to increase crash frequency. The overall effect of two left turn lanes on the major approaches was to reduce crashes by nearly half. The effect of one right turn lane reduces the crashes by a quarter. Lighting by a little more, just over 10%. So our net effect is a predicted crash frequency of 1.39 per year when we've applied these conditions for our specific intersection, which differ from the base conditions of the SPF. There are no CMFs in this first edition for signalized rural multi-lane intersections. There is some information in Chapter 14 of Part D, but it wasn't robust enough to make it into Part C, Chapter 11. It sounds strange, but it's literally the limitation of how much we know and how well do we know it in terms of the data sets that were available to make a robust regression line to develop a CMF that was robust from the analysis. Some additional CMFs that are over in Chapter 14 of Part D. You can use them individually. Be careful about combining them. Use them as an assessment of the safety treatment to assess the effect. For increasing the median opening width, converting minor road stop control to always stop control to signal control, left turn lanes on major approaches, right turn lanes on two approaches. For median width, the median width opening is the distance between the noses. The rectangle defined by median width and median opening length. It's a little bigger on a positive, as you come into positive offset alignment, which is illustrated in this example. And this is from Figure 14.9 in Chapter 14. The effects are shown in Table 14.17. For rural, four-leg, unsignalized intersections, a CMF of 0.96, all severities, would be a 4% crash reduction. And that is the available CMF for the effect of increasing the median width by an additional 3-foot increment. And that's shown under treatment on the left-hand column. If you did more than 3 feet, you would expect that this would be multiplicative for each 3 feet. So if you increase the median opening by 12 feet, you would get 4 times the effect, so it would be 0.96 times 0.96 times 0.96 times 0.96, or in other words, the CMF raised to the power, to get the overall effect for that 3-foot increment 4 times over. Minor road stop control to always stop control. For those locations that meet the MUTCD warrants for always stop controlled intersections is a combination of approach volumes and crash rate. So rural at the bottom, all severities. The CMF is big. It's a 0.52. That means it reduces crashes in comparison to a two-way stop by 48%. That's pretty big and significant. The potential crash effects of converting from stop control to signal control. In the rural environment, all types of severities, the effect overall is a 44% reduction in crashes, that is a CMF of 0.56. We greatly reduce, hence the small CMF value for right angle crashes, the severe ones, for installing the signal in the rural environment. But our left turn severity, our right angle and left turn severity, these are also positive things. But look what happens to rear end crashes, a 60% increase over what we had before. The decision by state DOTs and other agencies to convert stop control in the rural environment to signal control is a mixed decision always. Hopefully, we're reducing severe right angle and left turn crashes and trading those for additional, less severe rear end crashes. Not an easy decision, it never has been, but at least in Table 14-7, you can see what's at play, what's at work, and what the effects are. 2 left turn lanes on a major approaches to a two-way stop control rural intersection. And this is one of the few places where you'll see a CMF, but it's over in Part D, Chapter 14, for a 4-leg signalized rural intersection. Right turn lane on 2 major approaches to a two-way stop control rural intersection. And the effects are shown as a function of the range of ADTs, from 1,500 up to 40,000 on the major road, minor road from 25 vehicles a day up through 26,000. A right turn lane on 2 approaches. So that's 2 right turn lanes, even though it says a right turn lane up in the legend of the title. There's additional good information available that goes beyond what's in the first edition of the HSM. You can find it in a recently available, published electronically, available on the NCHRP TRB webpage for NCHRP 650. This is the work of Dr. Tom Mays and others at Seatree, Iowa, for high-speed expressway intersections. And I wanted to bring this to you. It's not in the HSM. You may expect to see it in a next edition to the HSM. The quality of the research was high. It was good. It assesses the positive effects of positive offset for left turn lanes, access density from TTI and J turns. So for these additional CMFs, or safety evaluations from NCHRP 650, they identified that before and after studies of crashes for positive offset left turn lanes, up to 100% reduction in left turn crashes. Typical crash reduction for angled positive offset left turn lanes for rural expressway intersections are around 70%. This is the conventional alignment of left turn lanes, which has negative offset, so that any vehicle that's in the opposing left turn lane blocks the view of the turning vehicle at the decision point of through traffic coming through and approaching the intersection at a high speed. By moving them over with an angled positive offset, we move the driver over closer to the point of the turn, less distance, less exposure in the turn. less time to be exposed, and most importantly, be able to clearly see, unobstructed, the vehicle approaching. And older driver research has clearly demonstrated this and been available for more than 15 years now. We're now seeing in NCHRP 650 the safety effects being quantified. The number of studies, the number of locations is not large yet, and that's what's prevented it to date from being in the Highway Safety Manual. So positive offset is being able to see unobstructed an oncoming through vehicle, a conflicting vehicle, not obstructed by the opposing vehicle in the opposing left turn lane. Some examples. Some additional, go back. Somehow it jumped a whole bunch of slides on me here. Let me get us back. Gene, can you back us up? I'm apparently hanging up here for whatever reasons. Can you back us up to about slide number 32?
Okay, we're on 32.
All righty. It's just me that's hung up here. Slide 32. This is an example of a angled positive offset left turn lane. The upper one's from Florida. The lower right is a parallel positive offset from Ohio signalized. Go to slide 33. This is an example at a signalized intersection, overhead span wire with backplates, signal head per lane, from Florence, South Carolina by South Carolina DOT of angled positive offset. That pickup truck you're looking at the back of has a very short distance that he's exposed to when he turns and crosses, much less than for the paralleling left turn lane alignment. Slide 34, if you would, illustrates an unsignalized stop controlled side street on South Carolina 327 in South Carolina, a design by South Carolina DOT, not with long tapers. Their tapers are rather shorter, and it's very cost effective. If you would advance us on to slide 36, some additional CMFs beyond the HSM for access density. The Highway Safety Manual indicates that there's certainly a trend between crash frequency and access management at or near intersections within 250 feet. In this first edition, they say that it's a quantitative information indicates a trend. They could not, from the information available, give to a rigorous CMF that goes in as a CMF value. If you'd advance to slide 37, Gene. So this information on slide 37 is from a synthesis by TTI for unsignalized rural and signalized rural intersections. The default number of driveways is 3. And advance to slide 38, if you'd be so kind. An example, for 4 driveways on the U.S. route and 3 driveways on the county route intersecting for a total of 7. 7 minus 3 is 4, and our value is 1.251 for the CMF. Now, those of you who have managed to make it through multiple of these webinars on the HSM, you should have a feel for now what's a big CMF safety effect and what's the small one. This is a big effect. This is 1.251 or 25% increased crash frequency as the effect of 7 driveways in comparison to 3. I'm going to advance to the next slide, and it does work for me. Gene, thank you. So our CMF, what happens if we have 8 driveways? What would be the effect of 1 more driveway? For those of you who may be involved as permit engineers in your district or for your agency, and somebody wanting an additional driveway within 250 feet either side of the road of a multi-lane unsignalized intersection. So we'd use our 4 approach CMF, plug in 8 for the number of driveways, And I'll just let you think. If the answer before was 1.251, and now we're going to have one more driveway, what do you think the effect will be? Will it decrease? Will it double, which would be selection B? Will it be real small, like selection C, or is it D? And the answer is why it's item D. So a 32.3% increase in crash frequency, going up from 25% more crashes, is the effect of one driveway within 250 feet of a rural multi-lane intersection. Now, this is not in the highway safety manual. This is beyond it. But it's a good working value that didn't make it into the first edition of the highway safety manual that will help fill your toolbox of analysis tools in working with rural multi-lane intersections. There's an additional feature that's well covered in NCHRP 650, and that's the J turn for expressways, where left turns are allowed in, but left turns are not allowed out. And the path to lead back through the intersection. Minor road traffic wishing to cross or turn left is forced to turn right. Make a downstream U-turn at a planned U-turn point, return back to complete their desired maneuver. This conflict point management strategy eliminates 20 crossing path conflict points at a typical two-way stop-controlled intersection. Some of the information from NCHR 650 for 4 locations in 2 states. And I want to call to your attention the effect on total crashes. These are huge numbers. To decrease total crashes by 91%, 53%, 47%, 69% this is a huge safety measure. Now, the issue is always in dealing with the public. This is usually a change in geometrics that's done after a protracted and long public hearing process, but it is a known safety measure, well documented in NCHRP 650, and I would expect that we'll see J-turns included with a specific CMF in the next edition of the Highway Safety Manual. So in this third of the 3 sessions on rural multi-lane intersections, we've described crash modification factors for rural multi-lane and applied them. And almost all of the CMFs, all but one, were for stop-controlled multi-lane rural intersections. We only indicated one from Part D, Chapter 14, for signalized rural multi-lane. And with that, I'd like to, operator, if you're still with us, I'd like to, Rosie, if we could ask if there are questions that people would like to pose to Tim, Gene, or I by telephone.
Thank you. If you would like to ask a question, please unmute your phone, press star 1, and record your name when prompted. Your name must be recorded in order for your question to be introduced. To withdraw your question, you may press star 2. Once again, if you would like to ask a question, please press star 1. One moment, please.
I believe Caltrans Traffic Safety 201 has raised their hand.
No one has has come through on the audio section as of yet.
Well, I have to say, Rosie, this is the first time we've ever had that happen in an HSM webinar in this series, that there are no questions by telephone. We did have a couple of questions posed in the chat pod. I believe Gene Apparano and Tim Taylor have answered the question that was posed by Albert. Gene or Tim, do you want to offer anything further?
I'm trying to find the question. It had to do with...
The question was from Pima County DOT, is there documentation about the related statements that crashes are not the result of bad drivers?
There's opposite of that. There's tons of research that shows that the majority of crashes that occur on roadways is caused by driver error in most cases. That being said, as engineers, the Highway Safety Manual gives us some tools and identifies some crash modification factors for some geometric devices or geometric conditions and traffic control conditions that allows us to implement these into the roadway segment or intersections that would hopefully help reduce the incidence of driver error. That's about all we can do. As long as we have roadways, there's going to be driver error, and just because there's a driver error doesn't mean it's a bad driver. Good people make driver errors just as well as bad, but there are things that we can do to make the driving environment safer.
Thanks, Gene. There was an additional question from Oregon DOT Planning. Is it possible to obtain more specific background info on the HSM data sets? And the answer is yes, and it's found in the documentation and in the references to each of the chapters cited for each CMF or SPF equation in the HSM. When you receive your published copy of the Highway Safety Manual from AASHTO, go to the references for a particular item, and it'll identify the research that supported the value, the relationship to CMF, and then you can go to the background and published papers identified to get that additional information. Other questions? Ricky Fitzgerald, will these slides be available to the attendees? And the answer is yes, in PDF form, and they'll be available in the file share pod that we'll post in the wrap-up room at the end of today's webinar. Are there additional questions before we conclude today's webinar?
There are no audio questions at this time.
I wish to thank everybody for your participation. I appreciate all of your kind and polite and professional attention to the material as we're going through each of the important and salient parts of the Highway Safety Manual. Tomorrow's webinar will be on HSM applications to horizontal curves. It will also be a later start, as was today's webinar, at 1:30 Eastern Daylight Time. If you have not already registered, Gene's provided to you a registration link in the thank you pod in the middle.